Problem set number 4, question number 1. So this particular data set is focusing on the not attending school column. And question number 1, part A, asks you for the equally weighted mean. So remember that the equally weighted mean is the normal mean. So if someone asks you to take the mean or to take the average, it would be that kind of thing. So it's the sum of the values divided by the number of values, or the equals average function in Excel. However you want to do it, it's the straightforward kind of normal, easy mean to do. So in this case, I use the equals average function. The unequally weighted mean is the more complicated formula, and that is where we have to take the value that we want. In fact, let's do the equation. So it is equal to the sum of the value you want times the weights, and then we're going to divide by the sum of the weights. So that's kind of our general weighted average or unequally weighted average formula. Technically, it's an equally weighted mean formula also, as long as W is the same for everything. That's why we say it is equally weighted. But it's kind of overly complex if the weights are the same. So generally, we only use this approach if the weights are unequal. It still works either way. So in this particular case, x is the value that we want. And so in this question, the value is the not attending school. And the weight for this question, or this particular, question number 1, is something you needed to determine. Pretty much always, if there is an option to weight your data using population, the population should be your weights. And in this case, we do have a column that is population. So that is what we want to use as our weights. Importantly, since this not attending school is the value that we want the average of, this cannot be part of our weights. We can't take this and divide it by something else to get a weight, because then we will bias our results. The thing that we want weighted has to stand alone by itself. So this is x, and the weights have to be something that has nothing to do with not attending school. It can't be any algebraic manipulation of that. So again, kind of going our default, if we have a variable that is population, let's use population as our weight. Not attending school is x, so we would multiply that times the total population for what's in link. So that is kind of one iteration. Then we need to add to that the next x times its weight, and add to that the next x times its weight. And really we just go all the way down, doing that kind of thing until we get to the end of the data and we sum all of those up. And then the last step is to add up our weights. So our weights was the population, so we need to add up all of these guys. Go all the way down to the bottom. We see that the total sum is about 4,000. So take our sum of that times that, plus this times this, plus this times this. So take all of that, divide by 3995, and we get 833.6. Alternatively, and as a shortcut, you can use the sum product function, which does as the name implies, we are adding the product, adding two things that we multiply. So we can highlight this row and highlight this row, and throw that into the sum product, and it will do this sum of x times w for us a lot faster. I don't think we explicitly talked about that in class. Maybe we did. Regardless, if you do that or if you do it by hand, doesn't matter. It gets you the same equation. Don't forget to divide by the sum of the weights. That puts everything where it needs to be and kind of scales things appropriately. And so now we have our normal average and our weighted average, or more formally, we have an equally weighted mean and an unequally weighted mean. So that is question 1A. 1B. Question 1C asks, well, clearly these are different, 65 to 833. Why are they different? Yes, we're using two different approaches. One has equal weights and one has unequal weights. But why does that matter? Why aren't they giving the same number? Or I guess you can think about it. What is the weighting doing that makes these values different? And here we have to go look at the data and see, well, what are my weights? Because clearly, if we have unequal weights, then it's the difference between the two means or because of the weights. So where in my weights do we have something that's a little weird going on? And hopefully it kind of jumps out that, well, Whitehorse has a lot larger population than anybody else. And so when it comes to weighting, since our weights are based on population, whatever the Whitehorse value has is going to have 10 times as much importance in a weighted mean because we have 10 times as many people in Whitehorse as we do anywhere else. Whitehorse also has the largest not attending school number. So not only do we start off with a large number, but we are going to give it a tenfold, 10 times more importance in a weighted scheme, or an unequally weighted scheme. So that's why the unequally weighted mean is so much higher, because we are amplifying the effect of Whitehorse, because that has so many more people in it. Since we're here, I might as well jump to question number 2, because it's just based on this table. So in question 1, we have the equally weighted mean, the equals average, and the unequally weighted mean, in my case using the sum product, but it's that x times w equation. If we do the same thing for the full-time variable and the part-time variable, we get those numbers, and you can look at them. And then part 2, I was just asking for a plot of that. Often it is easier to interpret data visually and to see, oh yeah, those orange bars are a lot bigger than those blue bars. So it's easier to interpret that visually than it is via the table. So I didn't care if you did this in Excel or by hand. Excel is pretty quick if your data is already in this format, but not everyone is as comfortable with Excel, so I didn't really care. As long as you got a plot that looked like this based on these values. And then lastly, for question number 3, the interpretation is not particularly interesting here, but I wanted to give you a little more practice and kind of emphasize that just getting numbers, just making plots isn't the end game. Ultimately, we want to be able to interpret our data. And the key points being the unequally weighted mean is consistently larger than the equally weighted mean. The relative height of the bars stays the same across categories regardless of what mean you used. Meaning, or to translate that, the full-time attendance has the highest unequally weighted mean. It also has the highest equally weighted mean. And this category was second for both of them. It didn't matter which mean, and this one was the last. And thirdly, I didn't expect people to calculate this, but it is a truth that even though the relative pattern is the same, so this is the highest, second highest, third highest, the actual percent change between the first and second and third highest is not consistent between means, because the unequally weighted mean have higher values, or perhaps we should actually say because the equally weighted mean have smaller values, the percent change actually ends up being bigger for these guys than it does for the unequally weighted mean. Then kind of highlighting the importance of being sure that you understand when you should use an equally weighted mean versus an unequally weighted mean, and the impacts of that. So perhaps you characterize your data better by using an unequally weighted mean, and that's almost always the case, but there are repercussions, and dealing with percent change in this case is one of those.